I'm gonna walk through the merge function for an array. So the merge function header would look something like this. It would take uh, a pointer to the first element of the array, the index of the first element of the left subarray, the last element of that subarray, and then the last element of the right subarray. So here we have an array. This is the numbers that would be passed in. The 4 would be at the index of left first, and the 25 would be at the index of left last, and the 12 would be at the index of right last. So we're going to go through this and we're going to start at left first and left last plus 1. So we're going to look at the 4 and the 9, and we're going to have like our merged function or merged array as we go. So looking at 4 and 9, 4 is less than 9. So 4 is going to go in our merged array. And then now we increment the left one and look at 8 and 9. 8 is less than 9, so 8 is going to go in the array. We're going to increment again. If we look at 25 and 9, 9 is less, so 9 is going to go in the array. Now we're looking at 25 and 12 because we're incrementing the right one every time we take something out of the right one. 12 is less than 25, so 12 goes in it. And now we're only left with 25. So if the other subarray is empty, then 25 is the only thing that can go in. And then here's our sorted list. So this is taking in two, like this original array was subdivided a bunch of times. This would be the final merge to get a sorted list. So that's why the left side is sorted and the right side is sorted. Let's look at the merge function for linked list. So this is the header that I used in my code. We pass in a pointer to a node A and A and B are going to represent the heads of their own sublists that are sorted already. So here is A, which is a sorted linked list, and here's B, which is also sorted on its own. And then we're going to put them together in sorted order. So the first thing we do is we compare the first element of each list. So we compare A and B. Since B is smaller, it's going to become the first pointer in our outcome. So we're gonna make a node right here, and it's gonna be the first one. So we've already looked at this one, so we're done with that. Now we're looking at 7 and 60. Well, 7's smaller, so 7's gonna be the next element in our outcome. And we're going to make sure 3 points to 7. So as we're going through this, we're looping through or going recursively, and we're assigning each new node as outcomes next and then incrementing outcome. So now outcome's going to point to here. So we're going to go here again. We're going to compare 12 with 60 this time. And 12 is smaller. So we're going to use that one. We're going to make a new node and outcome is going to point to it now. Or, well, no, because first outcome next has to point to it. So we need to set the next pointer of the previous element before we can change what outcome is. And now that we've set the next pointer, we're changing these. We're going to set outcome to the next one and then do it again. So this time we're comparing 21 and 60. 21 is smaller, so 21 is going to be the next element added to the list. First, we're going to assign it as the next of outcome. So now 12 points to 21. And then we're going to change what outcome's pointing to again. And now the only element left is 60. So 60 compared to an empty list is just going to be is just going to return 60 because that's already sorted. So, oh, I lost my cursor. Oh, there it is. So 60 gets added to the list. We update outcomes next, and now we have a sorted list. Okay, now I'm gonna explain the first quicksort algorithm. We're gonna go through this and compare J with P the whole way. So if J is greater than P, we increment J. If J is less than or equal to P, we're gonna swap I and J and increment both I and J. And here I'm saying the value at J, not the index J. And then at the end, if the index J is equal to the index of P, we're gonna swap P and I. So I and J are the indexes of the first element, and P is the value of the last element to start with. So first we're going to look at J and P, and since J is greater, we're going to increment it. Now J is less than P, so we're going to swap I and J. Our P stays in the same spot, but our I and our J both get incremented. So now 1 is less than 3, so we're going to do the same thing again. We're going to swap I and J. And then increment both. And this time 4 is greater than 3, so we're just going to increment J. And now that J is equal to P, we're going to swap P and I. Oh, sorry, that was the wrong one. So now our pivot is in the right spot, and we're going to do our next call using that spot. So we're going to call quicksort on the left side. So using the first element, um, which is at index 0, and then the element right before the pivot is going to be 1. And then we're also going to call quicksort using the element to the right of the pivot, which is at index 3, and then the end of the list. So that's going to be 4, index 4. Okay, so calling quicksort on 0 to 1, we're gonna have 2 and 1 as our thing. And our pivot will be at the end, our J will be at the beginning, and so will the I. So 2 is greater than P, so we're gonna increment that. And then once J is equal to P, that means we need to swap P and I. So we have 1, 2. And then P is going to be here and I is here. And then we're going to go look at the other one. It's going to be elements at 3 and 4. So we have 4 and 6 to start. Our P is here, our J is here, and our I is here. Since 4 is less than 6, there should be a swap, but there isn't. So then we're going to increment both. And now J equals P, and if we swap P with I, it just stays the same. So our list is now sorted here. So after these partitions have been sorted, our final array is going to be sorted. So 1, 2, 3, 4, 6 is our final sorted array. Okay, let's do Hoare's quicksort algorithm. So we start with a pivot on the first one. Our low index is going to be the index after that, and then our high index is going to be the index of the last element. And we're going to go through, we're going to check the high first. If h is greater than or equal to p, we're going to decrement h and move it to the left. If L is less than or equal to P, we're going to move it to the right by incrementing it. And if H crosses over L, we're going to swap the pivot with H and get it in its right spot. Otherwise, if we're out of moves, we'll just swap L and H. So first we're going to look at H. 8 is greater than 6, so we can move H. And 2 is not greater than 6. So now we're going to move on. L is 4, which is less than P, so we're going to move it. And now 7 is not less than 6, so we're going to swap L and H. Okay, so back to H. 7 is greater than P, so we're gonna decrement it. Now, 2 is less, so we're gonna increment it. And then now we've had them cross over, so we can swap P and H. So we're gonna get 2, 4, 6, 7, 8. And our pivot is 6, and since it's been swapped, we know that everything to the left is less than it and everything to the right is greater than it. So we can do the next function call. So we'll do quicksort again, and this time with, if we look at the indexes here, the left partition is from 0 to 1, and the right partition is from 3 to 4. So now we're looking at 2 and 4 on this side. Um, So we have our pivot here. We have L and H here. Um, 4 is greater than 2, so we're going to move H over. And H and L have crossed over, so we can swap P with H. So doing that means that nothing's going to move. P and H are going to be in the same spot. And then now this would do another function call, but it would do a function call with only one element. So we have an array from 0 to 1 here. So it would just call 1, 1. And that would just return the number. So this side has been all sorted. On this side, we have 7 and 8. We have the pivot here. We have low and high here. And 8 is greater than 7, so H is going to move over. 8 is not less than 7, so L is going to stay in that spot. And now they've crossed over, so we can swap P and H. But P and H are already in the same spot, so this is now sorted. There's going to be one more call with that last element, which is 4, 4. But since it's only one element, it's just going to return itself, so everything's going to be sorted. So if we combine everything at the end, we're going to get 2, 4, 6, 7, 8 is our final sorted list. Hi, here's my code for merge sort. I'm gonna show right away that it compiles and runs. Yeah, there we go. So here it displays the original list of numbers in a random order, and then the sorted list is in ascending order. And yeah, everything's working as it's supposed to, so now we can look at the code. Um, so starting at the top, I have a structure for the node. So to make my own linked list without using the standard library, I just made a structure for the node that contains the content of the node and a pointer to the next node. And I also included a constructor here. Okay, so the first method here is split, which splits a linked list into two halves. It takes in the pointer to the head, and it also takes the node pointer variables A and B, which we're going to use to use as the new heads of the two lists it splits into. So the first thing we do is we need to find the midpoint. And we can do that using an algorithm where you have a slow pointer and a fast pointer. So the slow pointer increments one at a time, and the fast pointer is going to increment two at a time, as you can see in this while loop. So that by the time the fast pointer reaches the end, since it's moving twice as fast as the slow one's going to be pointing to the middle. So this while loop is going to increment the slow going slower and the fast going faster until the fast's next one is a null pointer, which shows that fast is pointing to the last node in the list. So once slow points to the middle, you can set A equal to the head of the list because your first list is going to be the first half, and then your second list is going to be the second half, which is going to start at the node next to slow. So B becomes the head of the second list. And now we have two lists, and we don't return anything because we directly change those pointers. And also, since we're breaking the list in half, we have to set slows next to a null pointer. So here's the merge function. We're going to use this to merge two sorted linked lists into one sorted linked list. So you pass in A and B, where each of those is the start, the head of a linked list. And this is a recursive function. So we have a base case. If B or A is empty, you're going to return the other. So this will happen at the end of merging the list once you because you're like inspecting them one at a time. Once you get to the very end, then one of them's going to be null. So this will also happen if like two empty lists get passed in. So it takes care of that case too. And then the recursive case, we need to keep track of the outcome because we're going to be comparing each node to see which one's the smallest as we go. So first, we're going to start at the head of the list and we're going to compare the content of A with the content of B. And if A is smaller, then we're going to set outcome to A, and then we're going to set outcome's next pointer to a node that will be returned after we call this function again. And the opposite will happen if B is smaller, then we're going to call the next function using B's next. So we have like the difference in the function call here is A next or B next, because if we've already compared A and found that it's smaller, then we're going to compare the next one. We don't need to compare it again. So this is going to call over and over until the final function call where, like, let's say the last number A is smaller and we've reached the end of A, then we're gonna have an empty list for this left one, and then a list with maybe one or more elements in this one, or it could be empty, or probably couldn't. But it'll return that, and then when we get to here, if not A, it's going to return B. So the end of the list is going to be whatever's left in B. And then after that, then you're going to go back to each function because all these recursive calls happen before returning the outcome. So it's going to go back, it's going to go backwards through all the function calls, and you're going to end up with a sorted list with the two lists merged together. So now merge sort uses both of those functions, and merge sort will sort a linked list using, it'll take in the head and use the merge sort algorithm, and it's a recursive function. So we start with the base case. If the list is empty, so head is a null pointer, it's just going to return head, which is a null pointer. So if it's empty, just return null. And then if the head isn't a null pointer, but the next element is a null pointer, that means the list only has one element. So it's already sorted. You can just return head. So that's the base case. And then the recursive case is where we declare node pointers A and B, and we want to split the list that has been passed in into two lists so that they can be sorted. So the first thing we do is split it, and we already looked at split. it's gonna assign A and B to be the heads of smaller lists. And A, we're gonna call merge sort on each of those smaller lists. And then after we've sorted each half of the list, we're gonna merge it at the end. But where it becomes recursive is here, where it calls itself merge sort. So let's say like this is our first time going through, we split the list in half, and the first half starts with A. When we call merge sort with A again, we're going to go through here and then split it up again, and then call it again with a quarter of the list. And we're just going to keep going over and over, and it's going to happen for B too on every branch. And then finally at the end, everything's going to merge together using this function that we know will sort everything. So also, merge returns the head of the list that is sorted and combined. So we're going to return the return value of merge at the very end of this. And this merge sort function is just going to return the head of the list when we use it. So when we want to use all this in main, some helpful functions for it is being able to turn an array into a linked list is the first thing we're going to do in main. So I have this function to turn an array to a linked list. It takes in an integer array and the size of the array. And I had to pass in the size of the array because I found that if I just passed in the integer here, then the value A is going to hold a pointer to an int or to an array. So it's not, if I did the size of function of A, it would only return the size of a pointer. So it wouldn't return like the actual size of the elements in the array. So I really had to find the size of it out here where the numbers were still an array and not a pointer. So I found the size and I passed it in. And if the size is 0, just return null because it's going to be an empty linked list. And if it isn't 0, then we can turn it into a list. So we have to declare a head, and we're going to assign it with the first element in the array. And we're declaring a new node here for that. And then to iterate through the loop and assign next pointers for every node, that we're going to have a current declared, and we're going to start it on head and then increment it each time we go through this loop. So this loop is going to go from I equals 1 to the end of the array, and each time we're going to point the next pointer of current to a new node that's just been created at the index of where we are in the loop. And then we're going to increment current, and then we're going to keep assigning its next pointers. And by the time we get through all of that, we're gonna have like a whole list of nodes that point to each other. And we kept track of the head in the beginning, so we can return the head of the list. And then to display all the elements of a linked list, just pass in the head of the list. If it's empty, just return. And if it's not, we're gonna start keeping track of the current node, start it at the head. And then while current is not null, we just loop through all of it and output all of the content and increment as we go. So then finally in main, I just made a random array here that I came up with. It's not sorted. It goes like up here and down here and has some negative numbers. And this is where I find the size of the array by getting the size of the entire array in bytes and then dividing it by the size of one element in bytes. And then I had created my pointer to the head of the numbers list that I'm gonna make as a linked list. So numbers LL is the head of the list, and it's gonna be equal to array to LL of the numbers array. So that's gonna return this function call is going to return a pointer to the head of the linked list, which is going to go into here. So then when I want to display the list, I call display LL with numbers LL because it's a linked list. So If this displays properly, we know that the array to LL works too, because this function display LL will only work for a linked list. And then um, this is the part where we're going to sort numbers LL. So it's a linked list now. And when we call merge sort on it, it's going to return a pointer to the head of a new sorted list. So that's why I set it equal to that. And then after that, we just display the new sorted list using that same function. And yeah, I could even like change some numbers here and it'll still sort it again. Okay, there it is again. These are all in sorted order. It's just going up.